January 1943. Aberdeen Proving Ground, Maryland. Snow lies hard against the frozen earth, compacted by boots and truck tires that never seem to stop moving. Inside a low military building, the air is warm, heavy, and humming with tension. Long wooden tables are crowded with papers, pencils worn down to stubs, mechanical calculators clicking endlessly. Stopwatch hands tremble. Every second matters. Here, the war is not fought with rifles or tanks, but with numbers. Young women in pressed blouses sit shoulder to shoulder, eyes fixed on columns of figures. They're called computers because that is exactly what they are. Human ones. Their task is to calculate artillery firing tables. Pages of mathematics that tell a gun crew how far a shell will travel, how wind will bend it, how air density will slow it, how gravity will pull it back to Earth. One error means a shell lands short, or worse, on friendly troops. Outside, American artillery grows larger, faster, more powerful. New guns, new ammunition, longer ranges. Inside these walls, calculation time stretches into weeks. The war is accelerating. The mathematics cannot keep up. Somewhere between the clatter of gears and the scratching of pencils, a realization settles in, quiet, unavoidable, and irreversible. The United States Army is running out of time to think. And that realization will force a decision unlike anything the military has ever attempted, pushing the story beyond these walls and into the deeper currents of a world at war. By early 1943, the Second World War had become a conflict defined not just by manpower or industrial output, but by speed. Speed of movement, speed of fire, speed of decision. Across Europe, North Africa, the Atlantic, and the Pacific, battles were no longer static. Artillery ranges had increased. Aircraft flew higher and faster. Naval engagements unfolded across hundreds of miles of open ocean. Every advancement multiplied the complexity of warfare. For the United States, the problem was not courage or material. It was calculation. Modern artillery was no longer a simple matter of elevation and distance. A single shell's trajectory depended on dozens of variables: muzzle velocity, barrel wear, propellant temperature, wind speed and direction at multiple altitudes, air pressure, humidity, even the rotation of the Earth at extreme ranges. Each variable changed the path of steel through the sky. Each required precise mathematical correction. Before the war, firing tables could be prepared slowly, carefully. Months of peacetime calculation were acceptable. In wartime, they were not. When the United States entered the war in December 1941, its artillery doctrine expanded overnight. New guns were rushed into service. New ammunition types followed. Each combination required an entirely new set of firing tables. Thousands of pages of data per weapon system. A single table could require tens of thousands of individual calculations. The responsibility fell to the U.S. Army's Ballistics Research Laboratory at Aberdeen Proving Ground. The BRL had been established during the First World War, but had never faced anything like this. By 1942, its corridors were crowded with mathematicians, engineers, and clerks working in shifts that blurred days into nights. At the heart of the process were differential equations, long, nested chains of mathematics describing motion through resisting air. These equations could not be solved analytically. They had to be approximated step by step by hand. The tools were crude by modern standards. Desk calculators driven by hand cranks. Slide rules. Logarithmic tables. Each computation demanded absolute focus. One missed digit meant starting again. Even at maximum capacity, the BRL could not keep up. Calculating a single high-quality firing table could take 30 to 40 days. By the time it was finished, the battlefield conditions it described were already changing. This delay had consequences far beyond paperwork. Artillery accuracy shaped entire campaigns. In North Africa, inaccurate fire wasted ammunition and revealed gun positions. In Italy, mountainous terrain magnified errors. In the Pacific, naval gunnery depended on precise ballistic prediction across rolling seas. The war exposed an uncomfortable truth. Firepower was only as effective as the mathematics behind it. The Army attempted incremental solutions. More staff were hired. More calculating machines were purchased. Workflows were optimized. None of it solved the core problem. Human calculations scaled linearly. Were it not? By mid-1943, the demands were increasing faster than any expansion of personnel could match. New weapons were already in development. Longer-range guns, rocket artillery, advanced bomb sights. Each promised greater destructive power. Each demanded exponentially more computation. Behind closed doors, concern grew. Reports circulated quietly through the Ordnance Department. Delays in firing tables were becoming operational risks. Commanders needed answers faster than human hands could provide them. The United States had built factories capable of producing tanks by the thousands and aircraft by the tens of thousands. But when it came to computation, it was still relying on methods that had not fundamentally changed since the 19th century. And as the war ground forward, it became increasingly clear that the problem was not one of effort or intelligence, but of scale. The conflict had reached a point where human minds alone could no longer process the demands of industrialized war. And that realization would force the Army to confront a deeper question, whether thinking itself could be mechanized. By the summer of 1943, the Ballistics Research Laboratory had expanded into something closer to a factory than a research institution. Hundreds of women, many with mathematics degrees, others trained rapidly under wartime necessity, filled long rooms lined with desks. Officially, they were known as computers. Unofficially, they were the hidden backbone of American artillery. Their work was exacting. A single ballistic trajectory might require thousands of sequential calculations, each one dependent on the accuracy of the last. The process was divided into steps, distributed across teams, checked and rechecked. Errors were inevitable. When discovered, entire chains of computation had to be redone from the beginning. Time was the enemy. Despite working at full capacity, the BRL faced a mounting backlog. New guns entered service faster than firing tables could be produced. Some weapons were deployed with provisional data. Good enough, but not optimal. In combat, good enough could mean the difference between suppression and failure. The Army searched for mechanical relief. Punch card systems manufactured by IBM were already in use for logistics and accounting. Modified versions were tested for ballistic computation. They offered modest improvements in speed, but they were limited by their design. These machines excelled at tabulation, not continuous calculation. They could not easily handle differential equations or iterative processes without extensive manual intervention. Analog devices were also explored. Differential analyzers, large, gear-driven machines capable of modeling equations mechanically, showed promise. But they were slow, fragile, and difficult to reconfigure. Each new problem required physical rearrangement of components. Precision degraded with scale. Wartime demands outpaced their usefulness. Across the Atlantic, intelligence reports raised uncomfortable comparisons. German scientists had invested heavily in applied mathematics and engineering integration. Their fire control systems, while not universally superior, demonstrated a willingness to push computation closer to the battlefield. The fear was not that Germany had solved the problem, but that it might. Within the U.S. Army Ordnance Department, frustration hardened into urgency. Committees were formed. Memos circulated. The question was no longer whether improvement was needed, but whether improvement was even possible within existing frameworks. At the Moore School of Electrical Engineering at the University of Pennsylvania, two men were already thinking beyond those frameworks. John W. Mauchly, a physicist with a deep interest in electronic computation, and J. Presper Eckert, a gifted engineer, had been discussing an idea that seemed almost reckless. What if calculation were fully electronic? Vacuum tubes, long used in radios, could switch states far faster than mechanical relays. In theory, thousands of them working together could perform calculations at unprecedented speed. In practice, no one had ever attempted to coordinate such a system on the scale required. Tubes were unreliable. They burned out. They generated heat. No existing machine used them in large numbers for sustained computation. Still, the idea refused to fade. In 1942, Mauchly circulated a memo proposing an electronic computing device capable of solving complex equations at speeds unimaginable by human operators. The memo initially attracted little attention. It sounded expensive, risky, unproven. By 1943, risk itself had changed meaning. The war was consuming resources at a pace never seen before. Millions of tons of steel, fuel, and explosives moved through global supply chains daily. Compared to that, the cost of an experimental machine was almost negligible, if it worked. The Army faced a stark choice: continue expanding a human system already stretched to its limits, or gamble on a machine that had never existed. In a conflict defined by innovation, radar, code breaking, jet propulsion, the logic of the gamble became harder to dismiss. Somewhere between the mounting backlog of firing tables and the accelerating tempo of global war, the question crossed a threshold. The problem was no longer how to calculate faster. It was whether the act of calculation itself could be transformed. That question would soon draw together engineers, officers, and mathematicians under unprecedented secrecy, and set the stage for a decision that would redefine not only the war, but the future of human thought. Inside the calculation rooms at Aberdeen, the war felt distant but constant. There were no explosions, no shouted commands, no enemy in sight. Yet the pressure was unrelenting. The women who served as human computers worked 8, 10, sometimes 12 hours a day, eyes scanning endless columns of numbers. Precision was not optional. Fatigue was dangerous. Many were recent college graduates, trained quickly and placed into a system that demanded absolute reliability. They understood that their work had consequences measured in lives, even if they never saw the battlefield. A single miscalculated digit could send artillery fire off target. The knowledge sat quietly with them, day after day. There was pride in the work, but also strain. Repetition dulled concentration. Mechanical calculators jammed. Hands cramped from turning cranks thousands of times per shift. Supervisors enforced strict verification protocols, knowing that speed without accuracy was worse than delay. The war asked them to think faster than human minds comfortably could. And as the workload grew, so did the sense that endurance alone would not be enough. For artillery commanders, firing tables were as essential as ammunition. Without them, guns were blunt instruments. With them, artillery became precise, flexible, devastating. In Europe, the effectiveness of barges depended on rapid adjustment. Counter-battery fire, creeping barges, defensive screens. Delays in computation translated into rigidity on the battlefield. Commanders could not exploit new conditions quickly. They relied on generalized data instead of weapon-specific solutions. This reduced effectiveness and increased risk. As the Army prepared for large-scale operations, amphibious landings, airborne assaults, deep advances, the demand for responsive fire support intensified. Artillery was expected to operate as an integrated system, coordinated with infantry, armor, and air power. That integration depended on mathematics delivered on time. Mechanization had transformed production. It had not transformed thinking. Mechanical calculators were faster than pen and paper, but they still operated one step at a time. Each operation required human input. Each intermediate result required human judgment. The limitations were structural, not procedural. No amount of training could overcome the inherent speed of mechanical motion. Gears could only turn so fast. Cranks could only be spun by human hands. The gap between the complexity of modern weapons and the tools used to support them continued to widen. Technology had reshaped the battlefield. It had not yet reshaped the calculation that made the battlefield intelligible. That gap would force a reconsideration of how war itself was managed, leading naturally into questions of leadership, responsibility, and risk at the highest levels. Within the U.S. Army Ordnance Department, responsibility for the crisis could not be delegated downward. Delays in ballistic computation were now appearing in strategic briefings, not just technical reports. Senior officers who had spent careers focused on manufacturing and logistics were forced to confront a different kind of bottleneck, one rooted in cognition rather than supply. The leadership problem was not ignorance. It was uncertainty. No doctrine existed for electronic thinking machines. Funding such a project during wartime required justification not in theory, but in outcome. Failure would not merely waste money. It would consume time, personnel, and credibility in the middle of a global conflict. Yet the same leaders understood something fundamental. Every major American advantage in the war, mass production, logistics, coordination, depended on organization at scale. If calculation could not scale with it, the entire system would slow. The decision space narrowed. Conservatism meant accepting delay. Innovation meant embracing risk. By 1943, the balance was shifting. The German military was not omnipotent, but it was methodical. Its early successes in Europe had been built on coordination, timing, and technical integration. Intelligence assessments suggested that German scientists were aggressively exploring automation in fire control, radar, and rocketry. The V-2 program, still shrouded in secrecy, represented a future where mathematics directly governed weapons in flight. Even without full knowledge of its scope, American analysts sensed the direction of travel. Computation was becoming a weapon multiplier. The fear was not that Germany had already built an electronic computer. It was that the United States might hesitate long enough to lose the initiative in a domain that had not yet been fully defined. At a deeper level, the problem raised uncomfortable questions. Artillery mathematics translated directly into destruction. Faster calculation meant more accurate fire. More accurate fire meant greater lethality. Mechanizing computation risked distancing human judgment from human consequence. Yet refusing to mechanize meant accepting inefficiency that could prolong battles and increase casualties on both sides. The war offered no clean answers, only trade-offs. As these angles converged, human endurance, military necessity, technological limitation, leadership risk, enemy pressure, moral weight, the situation reached a point of inevitability. Incremental change was no longer sufficient. The system itself had to change. All that remained was a single decision, and once made, it would move the story from pressure to action, from theory to construction, and from doubt to the most ambitious machine ever conceived. The decision did not arrive with ceremony. There was no dramatic announcement, no public declaration of a technological leap. In wartime Washington, decisions of consequence were often made quietly, buried in memoranda and contract language. But in mid-1943, within the U.S. Army Ordnance Department, a line was crossed. The Army would attempt to build an electronic computing machine unlike anything the world had ever seen. The proposal carried the weight of risk. John Mauchly's original concept, refined with J. Presper Eckert at the Moore School of Electrical Engineering, called for a machine that would abandon mechanical motion entirely. No gears, no relays clicking open and shut. Instead, it would rely on thousands of vacuum tubes, electronic switches capable of operating at speeds measured in microseconds. On paper, the performance was staggering. Calculations that took human computers days could, in theory, be completed in seconds. Differential equations could be solved through rapid iteration, producing firing tables at a pace compatible with modern war. In reality, nothing of this scale had ever been attempted. Vacuum tubes were notoriously unreliable. Even radio transmitters using dozens of tubes required constant maintenance. The proposed machine would use tens of thousands. Heat dissipation alone posed a critical challenge. Power consumption would rival that of a small factory. Failure rates threatened to cripple continuous operation. Army engineers asked the obvious questions. Could such a machine run long enough to be useful? Could it be repaired quickly when components failed? Could it be programmed flexibly enough to justify its cost? Mauchly and Eckert did not offer guarantees. They offered probability, engineering judgment, and urgency. What persuaded the Army was not certainty, but arithmetic. Even if the machine operated imperfectly, even if it failed often, even if it only worked a fraction of the time, its potential speed advantage was so great that it could still outperform human computation. In April 1943, the Army approved funding for the project under the Ballistic Research Laboratory. The contract was designated for the development of an electronic numerical integrator and computer, a name chosen deliberately, emphasizing function over imagination. ENIAC. Secrecy followed immediately. The project was classified. Its purpose was narrowly defined: to compute artillery firing tables faster than any existing method. Broader implications were neither discussed nor encouraged. In wartime, ambition was framed in terms of necessity. Construction responsibility fell to the Moore School. Eckert took the lead on engineering design. Mauchly focused on logical structure and computational method. Together, they assembled a team of engineers, technicians, draftsmen, and mathematicians under intense pressure. Design began before solutions were fully understood. Circuit diagrams were drafted while component specifications were still evolving. The machine's architecture was modular out of necessity, not elegance. Units for addition, multiplication, storage, and control built as separate systems, linked by dense webs of wiring. There was no precedent for programming such a device. Instructions would not be stored electronically. They would be set manually through switches and plug boards by operators who would later become its first programmers. As construction plans solidified, the scale became impossible to ignore. ENIAC would occupy a room more than 80 feet long. It would weigh over 30 tons. It would contain approximately 18,000 vacuum tubes, 70,000 resistors, and miles of wire. The machine was no longer an idea. It was a commitment. And once steel frames began rising and components began arriving, the Army could not turn back. The war would not wait. Failure was not an option, but success was not assured. As work began in earnest, ENIAC moved from concept to physical reality, and the gamble entered its most dangerous phase. By late 1943, the Moore School no longer felt like a university facility. It had become a controlled industrial site. Windows were covered. Access was restricted. Uniformed officers moved through hallways alongside civilian engineers. Inside a long, narrow room, steel racks began to line the walls, bolted into place with deliberate precision. ENIAC was being built piece by piece, not as a single machine, but as a system of systems. Each accumulator unit, capable of storing and adding numbers, was constructed as its own cabinet. So with the multiplier units, the divider, the function tables, and the master control, the logic of the machine was distributed physically across space, forcing engineers to think in 3 dimensions. Signal paths were measured not just in time, but in feet of wire. Vacuum tubes arrived in crates by the thousands. They were tested individually before installation, their failure rates meticulously logged. Early fears proved partly justified. Tubes burned out, connections loosened, heat accumulated in unexpected ways. Cooling systems had to be redesigned mid-construction, with powerful blowers forcing air through the machine day and night. Power consumption rose steadily as more units came online. When fully operational, ENIAC would draw roughly 150 kilowatts, enough to dim lights in surrounding buildings. The Army accepted the cost. Speed had become more valuable than efficiency. By 1944, sections of ENIAC were operational enough to begin partial testing. Engineers worked in parallel, some refining circuits, others debugging logic, others learning how to operate a machine that had no manual. There was no established language for programming. Instructions were implemented by physically setting switches and running cables between panels. Programming was labor-intensive and unforgiving. Changing a problem meant hours, sometimes days, of rewiring. But once configured, the machine performed with astonishing speed. Accumulators cycled thousands of times per second. Iterative calculations that once consumed weeks collapsed into minutes. The first full-scale test runs were conducted under strict secrecy. Artillery trajectories were fed into the machine, and results were compared against hand-calculated tables. Discrepancies were examined carefully. In many cases, the machine exposed errors in the human data. Confidence grew cautiously. The true demonstration came in late 1945, as the war in Europe had ended and the Pacific conflict approached its conclusion. ENIAC was tasked with a series of complex ballistic calculations designed to push its limits. The machine ran continuously, its panels glowing softly, the sound of air rushing through its cabinets constant and mechanical. It did not stop. Hour after hour, the feared cascade of tube failures did not materialize. Individual tubes failed, but the overall system remained stable. Maintenance teams replaced components quickly. The machine resumed operation without losing coherence. The result was undeniable. ENIAC could perform in seconds what had previously taken human computers days. For the first time, the pace of calculation exceeded the pace of wartime demand. Although ENIAC arrived too late to influence the outcome of most World War II battles directly, its impact was immediate within the military establishment. Problems once considered impractical were now solvable. Complex simulations became feasible. The bottleneck that had haunted the ballistics research laboratory for years was broken. The gamble had paid off. Yet even as officers assessed ENIAC's performance in narrow military terms, a deeper shift was already underway. The machine was doing more than solving equations. It was redefining what machines could be trusted to do. As ENIAC's operation stabilized and its capabilities became clear, attention turned outward, toward how this unprecedented power would be used, controlled, and ultimately understood in a world emerging from war. The climax had passed. What remained were consequences. When ENIAC entered full operation, it did so without fanfare. There were no press releases, no public demonstrations. The machine remained classified, its existence known only to a small circle of military officers, engineers, and scientists. In the immediate post-war months, its purpose was still defined narrowly: calculation in service of national defense. Yet even within that narrow frame, the impact was profound. At the Ballistics Research Laboratory, long-standing assumptions collapsed almost overnight. Problems that had once been rationed, assigned only when absolutely necessary due to their computational cost, were now approached freely. Engineers began to ask different questions, not because the battlefield demanded them, but because ENIAC made them possible. One of the earliest beneficiaries was weapons development. Advanced artillery designs, previously slowed by mathematical uncertainty, could now be evaluated rapidly. Shell shapes were refined. Propellant behavior was modeled with greater fidelity. Entire families of firing tables were generated in a fraction of the time once required for a single set. Beyond artillery, ENIAC was soon applied to other military problems. Trajectory calculations for rockets and guided munitions were explored, anticipating weapon systems that would not fully emerge until the Cold War. Aerodynamic studies benefited from rapid numerical integration. Even weather prediction, long considered too complex for timely calculation, entered experimental discussion. Perhaps most significantly, ENIAC was used in early thermonuclear research. As scientists began to explore the theoretical behavior of nuclear reactions, the need for rapid, repeated numerical modeling became critical. Although later computers would handle much of this work, ENIAC marked the first time such calculations could be attempted at meaningful speed. The cultural shift within the military was subtle but decisive. Computation was no longer treated as a clerical function. It became a strategic capability. Officers who had once viewed mathematics as support work began to see it as a force multiplier, as essential as logistics or intelligence. This shift altered planning itself. Instead of designing weapons and then calculating their feasibility, designers increasingly calculated first, exploring possibilities through simulation before committing to physical prototypes. ENIAC enabled a reversal of sequence. Theory could lead practice at speed. At the same time, the machine exposed new limitations. Programming remained cumbersome. Reconfiguration took time. The absence of stored instructions restricted flexibility. These shortcomings did not diminish ENIAC's value, but they clarified what the next generation of machines would need to become. Within months, the Army recognized that ENIAC was not an endpoint. It was a beginning. As secrecy gradually loosened and wartime urgency gave way to post-war restructuring, the implications of what had been built began to reach beyond military walls, toward universities, industry, and a world preparing for a different kind of conflict. As classification restrictions eased in the late 1940s, ENIAC began to emerge from the shadows. What had been conceived as a narrowly focused wartime tool was now recognized as something far larger, a prototype for a new way of organizing knowledge, labor, and power. The first realization came quietly among scientists and engineers who saw ENIAC in operation. They understood that its greatest contribution was not speed alone, but generality. With sufficient reconfiguration, the same machine could calculate artillery trajectories, simulate aerodynamic flow, analyze statistical models, or explore physical systems governed by differential equations. The boundaries were defined not by hardware, but by imagination and programming. This realization reshaped institutional priorities. Universities began to establish computing laboratories. Government agencies allocated funding not for specific machines, but for computational research as a discipline. The military, entering the early years of the Cold War, recognized electronic computation as a strategic asset on par with radar and cryptography. ENIAC's design limitations directly informed its successors. Engineers sought to eliminate manual rewiring, leading to the concept of stored programs, machines that could hold instructions in memory and switch tasks without physical reconfiguration. This conceptual leap would define modern computing, but it rested on the credibility ENIAC had already established. The human legacy was equally significant. Many of the women who had programmed ENIAC, translating mathematical problems into physical configurations, had begun their careers as human computers. Their work bridged two eras, one where humans performed the calculations, and one where humans instructed machines to do so. In doing that work, they quietly shaped the foundations of software engineering. Within the military, planning culture evolved. Decision-making increasingly incorporated modeling and simulation. Commanders came to expect numerical analysis not as supplementary insight, but as a baseline requirement. The war had proven that speed of thought could be as decisive as speed of fire. ENIAC also altered the relationship between government and technology. Large-scale, high-risk research projects became acceptable under national security justification. This model would later produce nuclear weapons laboratories, space exploration programs, and global surveillance systems. ENIAC was among the first demonstrations that abstract theory, when funded and organized at scale, could yield transformative power. By the time ENIAC was formally unveiled to the public in 1946, the world had already changed. The war was over, but a new era of tension and competition had begun. The machine stood as a quiet symbol of that transition, built for one war, destined to shape the next. As ENIAC's physical components aged and newer machines replaced it, its influence did not fade. It diffused outward, embedded in institutions, doctrines, and expectations. What remained was not the hardware itself, but a shift in how humanity approached complexity, one that would demand reflection beyond immediate consequence. ENIAC's story is often told as a technical triumph, a triumph of engineering over complexity, but its significance runs deeper. It marked the moment when humanity acknowledged that some problems had outgrown human speed, human endurance, and even human imagination. For the first time, thinking itself became a task delegated, in part, to a machine. In the quiet glow of its vacuum tubes, a philosophical transformation took place. War had demanded it, necessity had justified it, but the consequences would ripple far beyond the battlefield. Calculation, once the domain of human diligence, became programmable, modular, and scalable. A machine could now anticipate outcomes, model scenarios, and extend the reach of human intellect. The implications were profound. Military planners, scientists, and engineers learned that the pace of knowledge could be accelerated not just by working harder, but by constructing tools that multiplied cognitive capacity. Humanity began to inhabit a world where abstract thought could be executed at near lightning speed. Speed was no longer just physical, it was conceptual. Yet ENIAC also raised enduring questions. The machine's power came with responsibility. Faster computation could save lives, but it could also amplify destruction. Delegating thought to machines required trust, oversight, and moral awareness. Lessons that resonate in every age of technological change. In the end, ENIAC was more than a machine. It was a threshold, a demonstration that the limits of human calculation were not natural boundaries, but challenges to be engineered away. From the frozen calculation rooms of Aberdeen to the sprawling racks of Philadelphia, one truth emerged. When humanity demands it, the mind can become mechanical and the machine profoundly human. The war had ended. The world had survived. But the future, already shaped by ENIAC, would never calculate the same way again.